Okay, this is Displacement 2.1. The picture, Figure 2.2. These cyclists in Vietnam can be described by their position relative to buildings and a canal. Their motion can be described by their change in position or displacement in the frame of reference. Position. In order to describe the motion of an object, you must first be able to describe its position. Maxine, please go somewhere else. Let me start over. Position. In order to describe the motion of an object, you must first be able to describe its position, where it is in a particular time. More precisely, you need to specify its position relative to a convenient reference frame. Earth is often used as a reference frame, and we often describe this position of an object as it relates to stationary objects in the reference frame. For example, a rocket launch would be described in terms of the position of a rocket with respect to the Earth as a whole, while a professor's position could be described in terms of where she is in relation to the nearby whiteboard. That's see figure 2.3. In other cases, we use reference frames that are not stationary but are in motion relative to Earth. To describe the position of a person in an airplane, for example, we use the airplane, not the Earth, as the reference frame. See figure 2.4. Displacement. If an object moves relative to a reference frame, for example, if a professor moves to the right relative to the whiteboard or to a passenger moves toward the rear of an airplane, then the object's motion changes. The change in position is known as displacement. The word displacement implies that an object has moved or has been displaced. In this text, the uppercase Greek letter delta always means change in, whatever quantity follows it. Thus, delta x means change in position. Always solve for displacement by subtracting initial position x0 from final position xf. Note that the SI unit displacement is meter, but sometimes kilometers, miles, feet, and other units of length are used. Keep in mind that when units other than the meter are used in a problem, you may need to convert them into meters to complete the calculation. Note that the displacement has a direction as well as a magnitude. The professor's displacement is 2.0 meters to the right, and the airplane's passenger displacement is 4.0 m toward the rear. In one-dimensional motion, direction can be specified with a plus or minus sign. When you begin a problem, you should select which direction is positive. Usually that will be to the right or up, but you are free to select positive as being any direction. The professor's initial position is x0 equals 1.5 m, and her final position is xf equals 3.5 m. Thus, her displacement is, and I know you can see those numbers, so I'm not going to read it because I'll just mess up, and you'll laugh. Okay, in this coordinate plane, motion to the right is positive, whereas motion to the left is negative. Similarly, the airplane's passenger initial position is x0 equals 6.0 meters, and its final position is xf equals 2.0 meters. So his displacement is, final answer looking like negative 4.0 meters. His displacement is negative because his motion is toward the rear of the plane, or in the negative x direction in our coordinate system. Distance. Although displacement is described in terms of direction, distance is not. Distance is defined to the magnitude or size of displacement between two positions. Note that the distance between two positions is not the same as the distance traveled between them. Distance traveled is not the total length of the path traveled between two positions. Distance has no direction and, thus, no sign. For example, the distance the professor walks is 2.0 meters. The distance the airplane passenger walks is 4.0 meters. Misconnection alert. Distance traveled versus magnitude of displacement. It is important to note that the distance traveled, however, can be greater than the magnitude of the displacement. By magnitude, we mean just the size of the displacement without regard to its direction. That is, just a number with a unit. For example, the professor could pace back and forth many times, perhaps walking a distance of 150 meters during a lecture, yet still end up only 2 meters to the right of her standing point. In this case, her displacement would be plus 2.0 m. The magnitude of her displacement would be 2.0 m, but the distance traveled would be 150 meters. In kinematics, probably didn't say that right, we nearly always deal with displacement and magnitude of displacement, and almost never with distance traveled. One way to think about this is to assume you marked the start of the motion and the end of the motion. The displacement is simply the difference in the position of the two marks and is independent of the path taken in traveling between the two marks. The distance traveled, however, is the total length of the path taken between the two marks. Checking for understanding. A cyclist rides 3 kilometers west and thus around and rides 2 kilometers east. A, what is her displacement? B, what distance does she ride? C, what is the magnitude of her displacement?